of methane gas, and this is for the formation of rust. So one happens really quickly, one happens really slowly. You don't feel the heat that's released from the formation of iron 3 oxide rust. And it's because of the speed. And a lot of time, it's the speed of a reaction that will harm you. You think about, dynamite. It's a lot of energy release, but it's not the heat that kills you. It's the impact, the force of the air around you coming into you, or objects flying into you. So, reaction rate. So it's the speed at which a reaction proceeds. Now, when we measure speed, we tend to do it at the very start of a reaction. And that's because there's no products to interfere with the reaction rate. You're just measuring at that point the change in concentration of reactants. Now, I don't know if you caught this, but rate is always recorded as a positive quantity. The left side of the equation is the negative side. The right side is always positive. So we use square brackets to represent concentration. So the concentration of product, let's say, could change. So you put the delta in front. So that's the change in the concentration of the product with a change in time. And this will equal some quantity. What is the units for concentration? Moles per liter. And time could be seconds or minutes, but let's say for this one it's seconds. So moles per liter per second. You can also write that moles per liter per second with a dot between. Can you see that? Now in this unit for kinetics, we're going to get some very bizarre units at some point. But it's only for this unit. All right. Change. So what happens to products as the reaction proceeds? If you were going to have a graph, you're going to graph concentration. So you've got concentration or change in concentration versus time. What would happen to your products? Where would it start? Where would it end? Negative slope, positive slope? Yeah.
Negative slope?
So it will go down. So your products are going to go down. So what you're saying to me is at the very start, you have lots of products and then they disappear.
Shouldn't it depend on the reaction?
What do you start a reaction with?
Reactants.
Reactants.
And then they go down to be the product.
They go down and the products do what?
They go up.
They go up.
355.
So this is your products. And then this is your reactants. Maybe it goes all the way down to 0, maybe it doesn't. But basically, you increase the amount of products, you decrease the reactants because they get used up. So, when it comes to writing out the expression for reactants, you have a negative because they decrease. So that means when you're figuring out your change in concentration, you will have a negative number, but you have a negative of a negative number, which makes it positive. So your final units will always be a positive number. What is the rate of production? Of ammonia. So ammonia is a product. We use little r for rate. So the rate is equal to positive change in NH3 with a change in time. It's always final minus initial. So we have 6.2 minus 3.5 over 4 minus 1. That's what, 2.7 mole per liter over 3 minutes. Thank you.
The answer?
Yes, please.
0.9 moles per liter per minute. So do we divide that 60 to get to seconds, or do we just leave it as?
You can leave it as minutes for this question. If a question asks you for seconds, then you would have to change it. Okay, so 0.9. Now you can write mole per liter per second, or have you seen this in math? Exponents of -1.
Yeah.
So that means 1 over, right? Yep.
That's for minutes, right?
Oh, sorry. Yes, we just had that conversation. Mole per liter per minute. So if you have the exponent -1, it means 1 over. You okay with that? All right, now that you know how quickly this was formed, how do you think we would figure out how quickly something was used up in this equation? Two words.
I just have a question.
Okay?
Isn't it 2 moles of ammonia?
Is it what?
Isn't it 2 moles?
Once you have information about one substance, you can figure out the rate of change of everything else using mole ratios. So we want to find the rate of change of hydrogen. Now, we know the rate of change of ammonia, bless you, and we know the mole ratio, bless you. So this is for NH3. So you're going to multiply that by 2/3 or 3/2?
3 halves? No, 2/3. 2/3? One of them.
Think about your NH3s. Do you want them squared or canceled?
Oh,
Or you want them to cancel? So 0.9 mole per liter per minute. That should be a dot. Times 2 NH3s and 3 H2s. So you're going to times it by 3 and divide it by 2. So what do you get? 9, 18, 27 divided by 2.
1.25.
1.35. So how does the rate of the disappearance of H2 compare to the rate of the appearance of ammonia? Slower or faster?
Slower.
It's faster because the number's bigger, but it's used up in a ratio of 3 to 2. So if you have the same quantities of a hydrogen and ammonia, you're going to run out of hydrogen faster, okay? All right.
How quickly it goes, it's how it forms.
So you know that, right? So if you take that, it'd be easier if I put it in. Times it by 1/4 to figure out how much oxygen, because 4 NO2s are produced for every 1 oxygen. And then times it by 1/2, and you've got the rate of disappearance of N2O5, yeah? Yeah. Okay.